Okay, so you're asking, let me share the screen. This is one of those, was it number nine you said this one?
Um, no, oh, maybe I had the wrong.
Well, sometimes it
Yeah.
randomizes.
Okay. That one I was able to figure out. I think maybe it was seven. That one was one that I did have marked. Maybe I was thinking of the wrong question. I think the other one was 7.8, 7.1, number eight, but that one's one I wanted to see as well. So that one
Okay.
wasn't the tangent line. That one was the one where, um, or maybe it is them fine. I don't know. I was able to use the help to figure it out, but so I ended up getting the right answer, but um, that one like kind of threw me for a loop. It was
Yeah.
number nine.
Um, I'm looking at number nine. I'm going to say this about arc length. Um, I'm not going to have you work out any of those rough integrals for arc length.
Okay.
I want you to be able to set them up. Let me make up a question. I'll give you an example of what I mean by that. Because this is something that comes up, it actually comes up in 267 as well. So I'm just going to make up a fairly easy question. All right, let me share the screen. Find the arc length of y equals x cubed over uh, between x and 1 and 4. Well, basically, the general formula is the Pythagorean formula. And so you put the y prime in here and square it. You get so you get 3x squared. But then when you square it, you get 9x to the fourth. So you have radical square root 1 plus 9x to the 4. Now, setting these up is easy, okay? But don't try to work these out. Just use calculator or Desmos.
Yeah, I did find in the ones where it was like that, where we were just having to set them up, find the A and find the B, even when they were giving us points and made them a little bit more difficult. It was just once I got to that other question, it was
Okay.
um
Well,
with the square roots and square.
as you have discovered
Okay.
in this class, radicals cause trouble with integration. Unless you get really lucky and you're able to do some magic algebra on the inside to square it away, you're generally facing an uphill battle with these guys. And believe it or not, this integral right here, there's no way to do it. There's no way to
Okay.
anti-differentiate it in common functions, no matter how hard you try. So, but I'm just going to
Okay.
mention this. When you get to calculus three, maybe you'll have it with me in summer session. Um, arc length
Yes.
in and of itself is not that interesting. We don't really care how long things are. However, there is a very, very useful application of arc length when we talk about parameterizing curves. And that becomes a very relevant thing um, when we get to like line integrals and surface integrals in Calc 3. So it's not so much that we like to know how long a curve is, but there happens to be a very useful relationship between the two types of parameterization that you'll see in multivariable calculus. Now, if none of that makes any sense at this point, don't worry about it. Um, it'll come up, you'll see it has much more of a relevance when you see it in context for some of the applications that we use it for. As far as I'm concerned, in this class, 99% of the battle is just getting it set up right. Get the bounds right, get the integrand right. You do that, you've essentially got the right answer. Okay. Do not
Okay.
waste a half hour of your life trying to work this out. Just go ahead,
Okay.
feed it into a calculator or Desmos, and just let it punch out some numbers for you. Okay.
Okay.
So
Thank
if you
you.
see a question like this on the test, or if you had it on your homework, in my attitude is that if you set it up wrong, then of course your number will be wrong. But if your number's right, that must mean you did all the setup right. That's really where the action's at.
Can you tell me what
Yes.
the exponents are in there?
Okay.
I can't read them.
Hmm?
Yeah, my thing is kind of,
If you pin it, it gets larger. It's the integrand with the bounds from 4 to 1, and then it's underneath the radical is 1 plus 9x squared.
9x to the 4.
Right. To the fourth, 9x to the fourth.
And that's 3x squared to squared, quantity squared.
Yes. So
All right,
right
thank you.
here, you're putting in the y prime. So the general form is 1 plus and then the y prime squared dx. That's the general form.
Thank you.
Sure. So Erica, I don't know if I answered your question.
You did. It's that we won't see something that difficult on the test, and
Well,
these the way that
you know,
you're.
I can give you a really nasty function. However,
Yeah.
it's not that hard to differentiate it and then just jam it into this setting right here. As long as
Yeah.
you're careful, it's not that difficult. And
Okay.
again, your calculator or Desmos will just use numerical methods to actually calculate a number.
Okay.
So I don't know. It's in the eye of the beholder. I mean, this is a fairly gentle function, y equals x cubed. And even then, that gives you a next to impossible integrand. All
Okay.
right. Is there any follow-up questions?
Um, did anybody else have a list of questions that they brought that they wanted to I don't want to keep asking over and over again if people are waiting.
Well, go ahead and
Yeah,
ask a question. People can always jump in.
Okay. So, seven 8.1 was number 13,
All
I think it
right,
was.
I'm going to it right now. All righty,
Oh, no, not that one. I got that one. No, it was 15 and 16. Sorry, either one of those, the ones with
gotcha.
the factorial numbers.
Yep, I see it. I'm going to share the screen. So let's look at 15 right now. Determine whether the sequence is divergent or convergent. If it is convergent, evaluate its limit. If it is divergent, if it diverges to infinity, state your answer is INF. If it diverges to negative infinity, blah, blah, blah. And if it diverges without going to either of the infinities, just write div. So what we got going on here, let's see, we got lim is n goes to infinity. And we've got this negative 10, factorial, and then 8 to the n. Okay, and then since I've got it up here, I'll write number 16 down. That's lim as x goes to infinity. What do we got? I don't know. Oh, okay, 10 to the 10 n factorial. And then we got n to the n. Okay. Um, so these are just sequences. These are just lists of numbers. And well, there's a few ways to do this. I'm going to unshare the screen. I'm sorry for the blurriness. I'm not sure what's going on. Okay, sometimes when I take it out of the direct light, it seems to help. Um, First of all, the negative 10 really has no role in this. All the actions happening with the ends. And it's a question of what outgrows what. Does factorial get bigger than exponential or the other way? Um,
The exponential would get bigger, right? Because your factorial is like that one time plus that. So
well,
wouldn't the
let me show you. Let's take n equals
yeah,
10. You'd have 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. Meanwhile, on the bottom, you have 10 eights, 8, 8, 8, 8, 8, 8, so 6, 7, 8, 9, 10. That's what you have. And the negative 10 out in front is not going to affect things. You can kind of,
yeah.
these guys cancel. These guys will obviously make something less than zero. but not equal to zero. This will just be some quantity. In fact, this will be a fixed quantity. Okay. Right here is where you start seeing the interesting behavior here because as n increases, you progressively get bigger numbers in the numerator than you're always getting eights in the denominator. So for example, the way I would
Okay.
argue this is that what I circled on the right will stay fixed. This will just be a fixed quantity. All right. It's not going to change. These eights don't do anything. And then now, as soon as n hits 9 and onward, you're gonna get progressively bigger values. You're multiplying by 9 over 8,
Okay.
then you're multiplying by 10 over 8, then 11 over 8, and 12 over 8, so on and so forth. So that's a heuristic argument to indicate that the factorial outgrows the exponential. So you're going to have a divergent um, sequence. Now, okay, this
And
negative,
then the -10 would come into play, right? Because then it would be negative
yeah,
infinity instead. Okay.
yeah. But the 10 itself has no role in whether it converges or diverges. Um, this one's a little interesting here because now you have this weird oddball function. And again, you can try out a few numbers. Let's try 5. On top, you'd have 5, 4, 3, 2, 1. And on the bottom, you're going to have 5 fives. Okay. And so these leading fives cancel, and you get here, you're going to get a quantity that's less than 1 at least. Actually, I wrote less than 0. It should be less than 1 right there. This will be less than 1. Okay. What if I did it for 10? So I have 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And on the bottom, I have 10 tens. Well, again, you can see that you're always going to get a smaller quantity on top than on the bottom. Do you see that?
Yes.
Because and now this is not staying fixed. Like in the problem here, this was staying fixed. Here, the bigger the n gets, the more of these terms you get, and frankly, the more terms you get that are less than one. So when you're multiplying a whole bunch of things that are less than one, you just make it more or less than one. And so it's going to converge to zero. Now the 10 here well, this would be 10 times zero. So basically it's going to converge to zero. So you have kind of an interesting hierarchy here. Um, exponentials, so you have polynomials, they're always less than exponentials. They're always, which are in turn always less than uh, factorials, which are in turn, this doesn't have a name. I'll just write n to the n. So there's a certain hierarchy in the nature of these classes of functions. And you can use this fact to help you with the sequences and series that you're going to be seeing in Module 8. So when you start seeing stuff like, you're going to get a question that'll be like some really ugly question. It'll be like 10, I don't know, n factorial times n to the 10th power plus n all over, make up something. How about n to the 2n? Something just horrible like that. Well, there are ways to do this analytically, but generally speaking, the polynomial part will almost become negligible. And so you're going to be comparing the factorial with again, whatever you call this guy. And I would surmise that the sequence that you see here will converge to zero. Now, whether the series converges is a different question. That's for later in chapter 8. But this little
So,
factoid is
a-
useful.
so
Go ahead.
bigger, as it got bigger than 10, right? That would be because we have n factorial, like as we're going to infinity, then the numbers to the left of the 10 would infinitely get bigger, and then the tens would all be the same on the bottom.
No, it wouldn't stay
So
10.
then we would,
It won't stay 10. This will change along with
oh,
this.
because it'll be 11 or 12 or 13.
Yes.
Okay, that makes sense. Okay,
So whereas this one's staying 8. Oops. This one was
okay, so
staying at
that's the
8.
major difference.
This one's actually changing with the power. And these don't have names. I wish they did. It would be useful.
So in the grand scheme of things, your polynomial. Okay, so I'm going to write down that list you have down at the bottom because it would be polynomial, then exponential, then factorial, then that
N to the N.
n to the n. Yeah. Okay.
So this is a general hierarchy on what outgrows what. So, like for example, you might have x to the 100th power and comparing that to 1.1 to the x. Okay. For small values of x, this is going to be a huge number, and this is going to be a small number. But eventually, this quantity here will outgrow this quantity here. And once that happens, it will always stay out. This will always be dominant.
Okay.
Alrighty.
Yeah.
Right now in
Okay.
8.1, all you're looking at are sequences. And that's just where you're looking at a list of terms. Later in module 8, you'll be adding them. That's where you get the series. And that's a different question.
Okay.
Now you're asking, does the series converge to a finite value? But it is good to have a general understanding of the relative behaviors of these classes of functions.
And then that cleared that up because I was definitely confused as to like how it flipped. So that made sense. And then 7.6, um the ones that took me the longest were the rope and the trough problem one.
Yeah,
I think that was number 4 or 8.
famous 7.6. Yeah, the bane of my existence. Um, I'm gonna share the screen. So 7.6. Let's see, which one, number 4, you said?
Yeah, so number 4, it was what, like setting up the thing for the rope and where it's at in the like over the edge.
Uh-huh.
That part I had to look up that I was like in the help section, so I
Sure.
didn't understand why the like minus number went from, like on mine I think it went from 3 to 4, on theirs it went from 3 to 6.
Huh.
um so I understood the gravity part, and I understood the like the setup of the equation,
Yeah.
other than why I was like why and how I changed that value. I was able to figure it out by modeling it from their answer. I was
Well,
just trying to figure.
let's just see what we get. Because I don't know. Sometimes I don't know what they're thinking either. Um, so a rope 50 meters long has a linear mass density of half a kilogram per meter and hangs over the edge of a building 80 meters high. And by the way, the building's height is irrelevant. It just needs to be higher than the rope. You know what I'm saying? Otherwise, it just lays there on the ground. So let me tell you what. I'm going to unshare and then, but I might go back to it if I have to. So the
Oh,
idea is
maybe.
this. Go ahead.
Um, sorry, it was this one was the one that I had issues with too, but the one where the numbers one that I was talking about was the pool one, the draining of the pool. That's
All
what
right, we can take a look at
was a
that one.
little. Yeah.
Did you want to look at the rope one? I mean, that was one I thought you asked for.
Um, yeah, the rope one, I don't I don't think that I needed that one done. That one, I'm sorry. That was the one
Okay.
that I was it was number 6. I just wrote down the wrong number.
All right.
I'm looking at work now.
All right. Well, let's do that one, and then we can always do the rope one if somebody else wants to see it worked out
Okay.
too. let's take a look at number 6. Let me reshare it. A circular a circular swimming pool has a diameter of 20 meters. That's a big pool. The circular side of the pool is 3 meters high, and the depth of the water is 2.5 meters. The acceleration due to gravity is 9.8 meters a second squared. Blah. The density of water is 1,000 kilograms per cubic meter. So I'm going to draw a picture. May not be exactly to scale. The diameter is 20 meters. The height is 3 meters, but the water is only filled to 2.5 meters. All right, so we're going to pump the water over the side. That's not the best picture. So what we're going to do is we're going to create slices of water. Okay, the thickness will be delta X. All right, so it's almost like I'm taking a slab of water. So that's basically a cylinder. It's a very flat cylinder. The volume is going to be pi r squared times the thickness, which is delta X. The diameter is 20 meters. That means the radius is 10. And so I'll plug the 10 here. It's 100. So I get 100 pi delta X. That's the volume. Now I need to multiply it by the density to get the weight, or the mass, I should say. So that's where the 1,000 comes in. So we're getting a big number here. We're getting what? 100,000 pi delta X. And then I have to lift it. And that's where I multiply by the gravitational constant, 9.8. So that suddenly we've got a really big number. That's going to be 9,800,000 pi delta X. And that's going to be what I'm going to integrate. Now, these can just be brought out to the front. But there's one more component that I need to build in here. I need to build in the height. So I need to build in the distance. So this top slab, maybe off to the right. Okay, how about right here? This top slab has to be lifted 0.5 meter. The bottom slab, so when we do this, if I were to do this for a whole bunch of slabs, I have to be lifted, well, it's going to have to be lifted 3 meters. And so what I need to do is I need to create an expression that gives me the change in the distance that they're being moved that corresponds with the bounds of integration. And this is where there's some freedom to make some choices. For example, it seems to me that why not just simply let the bounds be 0.5 and 3 and let the distances be, I have to be careful here. If I just put X, I think that's going to work. And by the way, the delta X just turns into dx. Let me think about this for a moment. It seems to me that this should work because this is representing the distance that the slab is being moved. It's literally like I'm just lifting up a whole slab of water all at once. So the top slab should correspond to a 0.5 distance. And sure enough, when I plug in, I get 0.5. And the bottom slab should correspond to a 3. And so this should work. And then I'll tell you what, I'll work it out here in a moment. But then to answer the other question, when it says pump all the water out of an outlet that's 2 meters over the side, So you're adding on an extra 2 meters. Well, it'd be the same stuff on the exterior. And again, you can play with some of the values. If I kept these distances the same, I would just need to add on 2 meters to the integrand. And again, it's got to kind of internally agree here. The top slab, which is at zero point 0.5, represented by x equals 0.5, needs to be lifted 2.5. And sure enough, that works. 2 plus 0.5 is 2.5. The bottom slab, which is represented here by 3, will have to be lifted 5. 3 plus 2 is 5. So that should work out just fine. I'll tell you what, I'm going to go ahead and just work out one of them.
Okay.
So it's going to be messy. I'm just going to punch it on a calculator, really. It's going to be a 2 pi. I'm going to have x squared, 3 and 0.5. I'll just worry about this right here. This would be 9, take away a fourth, which is what, 8.75. I'm doing this kind of quick. So then you're going to get a big number, 9,800,000 times pi divided by 2, and then all that times 8.75. And I get, oh wow, I get geez, 134,695,785. I guess that would be joules, right?
Yes.
That's a lot of joules. Um, that seems plausible because this is a lot of water. I mean, this 20 meters is a big pool. That's like 66 feet around or across the way. And yeah, that seems about right. Um,
So when they when they were setting up the equation, they had the 9.8 times the 1,000 because that was the gravity times the density, and then they had the pi r squared, and then
mm,
they put 3 minus x in rather than dx, and then you were just doing it from like the 1.5 to 0. So they were using the the height of the pool water for the top bounds and the 0 of it being empty for the bottom bounds. And then for the variable equation, they had 3 minus, well, mine was 3 feet, right? Like, because my sides were 3 feet and then
right,
my pool was
meters.
1.5 feet. So they had a, yes, or meters. My pool was 3 meters high, and then my height for my water was 1.5 meters high.
All
So
right.
they have like an x 3 minus x
Well,
in inside the
that's probably fine.
into
It it it
okay.
it that's the thing though,
Yours looks a lot easier though.
right. Well, actually, let me go back to the screen here. Let's some people like to just start integrating at 0. Let's say you just are comfortable with having that be your 0, where my pen is. Well, that would
Hmm.
be 2.5, right?
Hmm.
And then you would say, well, when I plug in 0, I still need to lift it half a meter. So I would have x plus zero point 0.5. That would be my integrand. If I put my bounds as 0 and 2.5, that would be x plus zero point 0.5. You could also set this at 0, and that gets a little awkward. If you set the bottom at 0 and this at 2.5, then when you're at 0, you have to lift it 3, so it'd be 3 minus x, and that would agree with the bottom bound of 0, and then top bound of 2.5, 3 minus x.
Yes, that's the way
Yeah,
that they have it set up.
it seems to me it's the same thing. It just needs to agree because what you're seeing here is this is the distance being that the water is being moved. All this other stuff is just going along fine. The dx is the thickness. All this stuff has to do with the density and the gravity and all that. Um, you're just trying to move. I set it up so that this top slab gets moved zero point 0.5 meters. Well, at zero point 0.5, and I plug it in, I get zero point 0.5. And the bottom down here at 3 meters, when I plug it in, I get 3. It has to be moved up 3 meters. Ignore this little spout for now. So at 3, it gets moved up to 3. So it seems like all we're doing here is we're just creating in shifts. And it seems like it still should just work just fine.
Yes, I think that that was a much clearer explanation of what I'm doing with the bounds and what my values are,
Yeah.
because that was where I was confused as to how we got to the numbers with the, 4 minus X or 3 minus X. And so that was the height of the pool. And then we're going down to the water and it's being pumped up from whatever that height is
A lot of it
to the
has
3 feet or to the.
a lot of it has to do with where you decide you want your origin to be. You can put your
Okay.
origin down here. You can put it at the top of the water level. You can put the origin at the top of the pool. If you have a spout, you can put the origin up there. You can put the origin way up here if you wanted, as long as you build in the shift. Um, as long as you're careful and you just kind of make sure that everything matches up. So you know that when you're at, like I had it at zero point 0.5, I wanted to lift it zero point 0.5. So this should give me zero point 0.5. When I plug in zero point 0.5, I get zero point 0.5 and so on. You could work this out laboriously. I mean, this would not be that hard to do. What if you made 10 slices? So you went from like zero point 0.5, I don't know, 0.75, 1, 1.25, and so on. You can actually work them out just numerically and then add them up. It'd be tedious, but it wouldn't be that hard like a Riemann sum. And it should work out just fine. And again, this is a big value, but then again, this is a big pool. Water is heavy. You're lifting, I mean, think about 1,000 kilograms for a cubic meter of water. That's over a ton.
Yes.
So yeah, I would expect it to require a lot of joules to lift up that water. I hope this helped.
That helped a lot because it let me see that, like, it's almost like your con it's almost like your regions are the same. Like if your equation's the same and then you have a different constant at the end, the area between the regions, as long as the constant at the end is the same, is going to be the same, right? So
Yeah.
you, that because this it's kind of the same thing. You're setting up the equation and you've got the volume of water and you can set, like, you're explaining that you could set up the origin wherever you wanted, that as long as your bounds match what the diagram that you're creating, that helps a lot because it puts into perspective what those bounds are
Hmm.
and what we're doing with them. It just gave me a little bit more of a concrete example,
Okay.
so that was helpful. Thank you.
Yeah. And one of the things about when you go to the help, are you doing this in Infinity?
Yes.
Um, just be aware that I don't know, whoever created the help sometimes I've noticed has somewhat of a dense way of writing things. It's not incorrect, but it can be very, very difficult to digest.
Breach.
Oftentimes they don't match the way that the video taught us how to do it. So
Right.
it's like there's multiple ways to skin a cat, and then it,
Well,
it's very confused. It's very confusing because I'm like, okay, sometimes their way is easier and sometimes the video way is easier, but when you're trying to apply it to the problem, it's really easy to just plug in the numbers, like you're going, okay, this number matched that number, this is where this goes. But then I didn't know why.
well, don't get discouraged.
Okay.
That's where maybe an alternative explanations in order. You can always, I've noticed there hasn't been that much activity at ed discussions. If you ever encounter something like that where the explanation just seems weird, put it onto ed discussions and I can usually go in and figure out what they're trying to say.
Okay. And
Charles, did
then
you have a question?
No, I just said I was just telling you guys to preach on that because the
Oh,
applications of physics and engineering pieces was pretty difficult for me, and going through those explanations were, they kind of skip some steps, so you almost have to sit there and figure out,
oh
okay,
yeah.
how did they get from this step to the next step? But as far as that actually was going to be my question, is the on the applications of physics and engineering on the test. You got any tips for work through all the problems on the homework, but Do you have any tips for ones we should study for the test or any other?
Well, the tip I'll give you is that the questions on the test are chosen from the same master set as your homework.
Okay.
You'll probably see the same question. It might have a different number, but if you can make that adjustment, you should be fine.
So similar to the last test, our best review source is to go back through, do the Edfinity problems over and over again, and then also do the practice similar problems.
Yeah, as much as you can.
Okay.
Because again,
All
when the
right.
tests are created, there's a master bank of questions, and then we just simply create a test from that master bank. This is the same superset as your homework set. So you literally will have seen the entire test if you did all the Edfinity questions.
Okay. Um,
I have a kind of a question for you. It's not one of the assignments that we did, but it's in the review. It says not for credit, chapter 7 review
On
in the,
Edfinity.
yeah, on Edfinity.
But I still want you to do it because let me scroll to it. Yeah. Are you talking about the chapter 7 study notes?
Yeah, when it goes through and kind of gives you like a brief like explanation of how to, and then it gives you a bunch of examples.
Yeah,
There was one thing like I understand the shell method and like it's actually it's not rocket science, but
right.
in the examples, I got kind of confused with so, I don't know if confused is the right word, but what they were doing. Like when you look at the examples that they give you there for the shell method, like when it rotates, let me find it. I just lost it. Like rotating on the y-axis, like you get um, y equals x squared and y equals 4 about the y-axis. Understand how it works, and I understand like it's opposite of the way the washer and disk
Right.
method works. But like in that first example, like you get the 4 minus x squared, which I understand why they did that because you
Okay.
have the y equals 4 and the y equals x squared. Totally understand it. I get it. But then when you go down to the next example, like you have the x to the 3 halves and the x to the equals 4.
Right here.
Yeah, but they only use instead of doing like y minus 4 or it's just y times the one curve. And I noticed it somewhere else in the examples they were using where the the equation that they saw like they're using y as the it's solved for x
Yeah.
doesn't do the minus where the one that's solved for y does. And I'm not really sure, like that kind of caught me off and threw me completely off.
are those because y equals 0 in those equations?
Let me let me see what's going on here. So
Because the region is bounded by y equals 0 in that case, and the other ones, the region is bounded by y equals 4. So I think that you have the
hmm,
4 minus on the other one where you don't have it on.
yeah, this one, the example one's going around the y-axis. Example two's going around the x-axis. And they want us to use shells, so we'll do it using shells. Um, so I've got example two up. Is this the one you were asking about, right?
Yeah. Yeah.
Okay,
So
so
between that one and the other one, like I know why the 4 minus x is there.
so I'm going to draw the picture. Y equals x to the 3 halves is, well, it's kind of a curve that looks like this. It's curvy upwards. X equals 4 is going to put us out here. The x-axis obviously is here. And we're going to integrate, or we're going to rotate around the x-axis. So we're going to end up creating a shape that looks like kind of like a horn. Okay. And so they want us to use shells. All right, we'll use shells. Um, because frankly, you could use discs here as well. Actually, it'd probably be easier to use discs. If we use shells, what I'm going to do is that means I have to integrate with respect to y, and I'll just draw a representative shell. How about this guy right here? So that's what happens is a representative thickness, and then that gets rotated, and that creates so I'm just going to draw essentially a shell. See if I can do this. Yeah, there we go. That's not too shabby. You see how this little guy when rotated makes one of these?
Mhm.
And so now if I lay this thing flat, I get a really long, basically a rectangle. And it's going to have a little bit of thickness to it. Okay. And so I just need, so the dy is actually going to be the thickness. So the volume of this is just simply the length, width, and height. And that's where this is where the pi and the equations start coming in. We're integrating, well, let's see, when x is 4, and this is the equation y equals x to the 3 halves, that means this is going to be 4 and 8. Because when you plug in 4 and you take the square root, you get 2. 2 cubed is 8. So that means we're going to integrate from 0 to 8. And I'm integrating with respect to y because the thicknesses are on the y-axis. So I need to convert everything back and take this equation here and write it where x is isolated. So that just simply means y to the 2/3 power. Okay. Um, so now we've got two things going on here. From the axis of rotation, draw an arrow up to the shell. That's your radius. That would be like the radius up to here. And that's going to be the y value. That's just simply y. Okay. And that means when this thing is spread out, the long side here is actually the circumference. So the circumference is 2 pi y. So I'll circle that. So 2 pi y and then the dy. And then the length here, this kind of this distance right here, which becomes this distance right there. This is where we get into where the equation comes in. It's going to be 4 minus x, but x gets replaced with y to the 2/3. So that's what this guy is for. Is that so? When I'm taking the volume of the shell, this length, width, height, well, let's just piece them together. I've got 2 pi y, 4 minus y to the 2/3 dy. And that is my general formula for the volume of a representative shell. And that's what ends up getting integrated. And that's where the 2 pi can come out in front. We have y and then 4 minus y to the 2/3 dy 0 to 8, and that should work out. I would distribute the y through, just do power rule a couple times.
So that's exactly what I did. But
Yeah.
if you look at the example, like the 4 minus y to the 2/3, they
Okay.
just have as y to the 2/3.
Oh, yeah, that's an error.
They have a y times y to the 2/3 dy, and then they have 2 pi in the bounds of 8 to 0 equals y to the 5/5 dy.
Yeah, that's an error.
Okay, so
Okay.
I was doing it right, but the thing is wrong.
Yeah, you know what? Give me a moment here. I'm actually going to
That
I'm gonna,
makes me feel so much better.
well, I don't want to confuse you and everybody, so give me a moment here. I'm actually making a screen capture of this one. I'm going to send it to our people and they can fix it. I'm very sorry about that. All right. This shape right here, if I redraw it, I'm going to set my pen down. I can't find it. I'm just going to say this in general. If this is the shape that you're revolving around the x-axis, discs work a lot better. Discs is much easier. It's it's the integral of pi r squared, so pi, and then integral. This will be 0 to 4. Um, we have dx, and the radius is just simply the height, so it'd be uh, x2. What was it? 3/2, and then you have to square that. Okay, that's not a hard function at all. That's easy. So you know what? These should give you the same answer. I'm not going to work them out, but these should give you the same answer. And this is one of those times when I would go with disks. Now, if you're asked to do shells, do shells. But a lot of times you just simply ask to find the volume. So you pick. Shells, there's sometimes when it's algebraically difficult to use disks, so that's when shells comes in handy. All right. Um, yeah, I'll get that error fixed.
No, I appreciate that because that threw me off for probably a good 20-25 minutes this earlier today. I'm just glad I was kind of working it out right and not
Yeah.
looking.
Well, yeah, errors are regrettable. It's easy to make them, but it's easy to fix them too. So I can send it to the right people. It'll probably be fixed by 9 o'clock tonight.
Awesome, thank you.
Sure. Um, we have time. I got 6:51 Arizona time right now. Maybe we can do another question. Anybody want to try to confuse me more?
Let me see. The, I think the two that I had are either 7.3 number 2 or 7.4 number 5, either one of those.
Um, oh, I got 7-3 going, so let's take a look at that one.
Okay. Number 2 is one of them with a roller's number.
Yeah, this is all right. I'm gonna give me a second here. I sure lost it. I'm sorry. Was it 7-3 number 2? You said.
Yeah.
All right. 7-3 number 2. Use the method of shells to find the volume generated by rotating the region bounded by y equals e to the negative x squared, y equals 0, x equals 0, x equals 1 about the y-axis. All right, whatever. All right, so again, I always find it, I have to draw the picture. I can't do it otherwise. The e to the negative x squared is actually the famous bell curve. You've got y equals 0, which is the x-axis. You've got x equals 0, which is the y-axis. And then you've got x equals 1. So we got this region right here, and we're going around the y-axis, and they want us to use shells. And so if I draw a representative shell, so I draw a representative thickness, and remember I've got a couple things going on here. I've got a radius of x from where it goes from the axis of revolution. So the axis of revolution is the y-axis. I'll make that really dark. You've got a radius of x, and then also, okay, the height is y equals e to the negative x squared. And so remember, you've got the thickness is the dx. When this thing gets spun around and creates a shell, and you snip it and lay it flat, you get the circumference. So the circumference is just 2 pi x. And then the width of that long strip that we talked about is this guy right here, e to the negative x squared dx. And then you're just going to integrate that from 0 to 1. I went ahead and put the 2 pi on the outside. In this case, shells is really the only way to work this problem. If you try to do it using disks around the y-axis, this part's easy because it's just a block. But this part right here would present some really difficult algebra, and you'd quickly find that it just can't be done. So shells is really the only way to do this one. And this integrand will integrate using substitution. So I'll leave that for you to work out. And then since we got a little time, we'll go to that other one you asked about. It was 7, 4. Which number was it?
7 for number 5.
All right, let me
That's
do a
the one
quick.
with an arc length with a natural
Yeah.
line.
All right. And again, I'll it's a good reminder on this one. Let me share the screen. Seven, four, number 5, find the length of the arc formed by this function y equals 1/8. We've got negative 4x squared plus 2 natural log x. Oops. And from 3 to 7. All right, so the general formula is just which 1 plus, and then the radical, I'm sorry, not the radical, the derivative squared. Okay. Oh, all right. So if we do the derivative here, we get, on the inside, we get negative 8x. So we're going to have negative x. And then here we're going to have 2 over x. So it'll be 1 over 4x. That's the derivative. Now that, believe it or not, will actually work out. If you were to do this by hand, it'll take you about a dozen steps, but this will eventually work out to be a perfect square, and in that case, the square root cancels it. But this is a highly contrived function, okay? And like I said earlier, a question like this, 99% of the battle is setting it up. Set it up correctly. That's purely procedural. Just follow the recipe. If you set it up correctly, let Desmos or some other calculator, whatever, do the calculation. Okay.
Okay.
Life is too short to be working these things out by hand.
Okay.
And like I said, when you get to Calc 3, you'll see why this arc length integral is so important. It's hard to explain now without going through a couple of lectures of multivariable stuff, but once you get there, and if you have me, I usually make a big thing about it. I tell students I don't really care how long an arc is. What I do care is that you're able to understand how to set it up because of the applications that will follow. Okay, so I'll leave it at that. Now, if you saw this on a test and all they want is a number, and let's say you put it on Desmos and it gives you, I don't know, just make a number 17.567, and you get it right, I'm not going to know how you did it. But you know what? If you get the right number, that tells me that you must have set it up right. And that's really what I want to know. So if you get the right number, that's just a quick and easy way that I can reverse engineer and say, you must have done it right. There's no way you're going to randomly guess that number.
Okay. And then you put the announcement to purchase the book. And I had the digital book for the newer one, and I did go on and buy one of the used physical copies.
Mm-hmm.
You said within the last 10 years, I ended up getting 7E, which is it was done in like 2012. So
That's
it looks
fine.
like it's a lot of the same
Yeah,
information.
I
It's
mean,
just organized different.
yeah, that's the thing. The math itself doesn't change. The ordering within the book might, as long as you're able to match them to, if suddenly it's section 13.2 and the old book was 11.4, as long as you're able to match them, you'll be fine.
Yeah, I was able to match the titles with them.
Okay.
Like all like I think section 4 in theirs is section 6 in ours or something. Now they've just rearranged it, but I was just checking to make sure just because you said like within the last 10 years, and then when I saw the copyright on the 7th edition and they're on the 10th edition, the
Yeah.
7th edition's copyright was 2012, so it's like 15 years old.
Well, 15 years ago, we were using the same numbers and the same integral symbols and everything.
That's what I figured. Okay,
Um,
perfect.
I mention this because I still believe that working problems out of a book the old-fashioned way is the way to go because you just need practice. A lot of the issues that students face at this level, it's not so much that they don't understand the material. I think a lot of students do understand the material. Then I think it just boils down to repeatedly doing the actual work until you start to master it. And Edfinity just simply doesn't have enough questions.
Yeah,
Ideally, each one of these Edfinity sections should have about 60 questions.
yeah, you get through like sometimes there's only two on certain sections, or there's like four, and once you've done all those, then you're just repeating the same question over and over
Yeah,
again that you've already worked and have the answer. So that's why I had the digital book, but I don't like working off of digital books. I prefer a paper copy. So when
yeah.
you recommended to get an older one, I'm like, okay, well then that's not $200 for a textbook. So I'll go
Right.
ahead
It's like
and
what,
buy
like
it.
$10, right?
Yeah, I got it for $15 on Amazon and they shipped it the next day.
That's fantastic. And it'll probably be a book that you'll keep for a long, long time because it's like having a dictionary. 5 years from now, you're in grad school and you need to look up an integral that you forgot about. Um, so as you can tell, I'm pretty old. I was alive in the 1900s. So I still think that the old-fashioned way of just lugging around a book, working problems with pen and paper and the TV on and your cat on the desk is the way to do it. Just practice, practice, practice. That's what it takes. You got to do a whole bunch of them before it starts to really click.
Thank
So
you.
I hope you see benefit from it.
I do. I appreciate it, and I really like the idea of having the actual book, and they have reference pages on both bookends, one for algebra and then one for calculus. And
Mhm.
so there are tear out sheets that the person who had it before me didn't tear them out, and I won't either. I'll just photocopy them, but they're very useful.
All right. Well,
Yeah.
good, good. I hope,
Thank
and again, if you're going on to Cal 3, whether you have it with me or not, having a book is just a good idea. And I hope you just tackle them.
thank
So,
you.
well, guys, it is 7 o'clock my time. It's starting to get dark outside. I'm going to go ahead and power down here. This video will be um, on the web probably in about an hour. Um, and good luck tomorrow on the test. And if you have any questions between now and then, put it on Ed Discussions, and we'll go
Okay.
from there.
And even though the test opens up at 4 o'clock on tomorrow, it is it is still going to be open until midnight on
Right,
Monday, correct?
30.
Just
You
like
get
okay.
32 hours. Right. In fact, I'm going to be
Okay.
gone for
And then
about half that. I'm going to be gone
sorry,
about half
someone
that
in
time.
the
I have to head back to Tucson, so but I'll be back Monday night to kind of shore up things, and I hope to have grades circulated. I'm going to try to do them pretty quick, like probably Tuesday morning. And
and then someone was asking in the chat how many questions are on the test,
well,
if you
I'm
know
not
how
going to
many there
reveal
are.
that. It'll be a surprise.
Oh,
So
all right.
again, do your infinities. You'll have seen the test. So
Okay.
all right, everybody. Good luck. Bye bye. Five, four,
Bye.
three, two,
Thank you for everything.
one. Bye.